Let me get back to the examples, okay? So for example, if I want to prove, oh boy. Okay, so if I want to prove that n+1's cube is more than 3 raised to power n for all n between 0 and 4, you would do it by exhaustive proof. Okay, you would try to solve it for 0, it's true, for 1 it's true, for 2 it's true, 3 it's true, and 4 is true. Okay, you don't need to do it for 5. That's enough to prove the statement for you. Yeah. कहाँ पे? Oh, यहाँ पे कह रहे हो. Okay, this is 3. Okay, sorry, this is a typo. Yeah, this is 3. n+1 raised to power 3. Good catch. Okay. Are you part of this class? You're late. Go away. Okay, so cool. Is this clear? Okay. Proof by case. So if n is an integer, then n square is at least n. Okay, how do we prove this? You have a question on the previous slide? Oh, किसको नजर नहीं आ रहा? आगे आ जाओ. Hurry up. I'm looking for people to come up. All right. How about this statement? How are we going to prove this?
By taking like random numbers.
Okay. Okay, that's the answer I was looking for. It's a wrong answer. It's a terribly wrong answer. But this is the answer I was looking for. Okay. So the thing is, देखो, the set of integers is infinite. Okay. So this statement is infinite different n values. If you prove it for 10 or 20 or 200 different values or 2 billion different values, that will not prove this statement. Okay, keep that in mind. You can prove it for 2 billion different values. That statement still remains unproven because this is a statement about an infinitely large set. That's not enough कि हमने देख लिया पहले 2 billion integers को, and this is the pattern that we see. So this statement must be true. That's not enough. Okay, this is a mistake people make a lot during this whole degree, I guess. But if you have a statement that's true, that's saying this is true about the whole of the set, you have to prove it for the whole of set. You cannot leave one single possibility. So how do we go about doing it? Okay, so domain to define हुए, domain is and is integers. Okay, बोलो कैसे करें? Sure. But then that would, okay, so that would prove that this statement is true for first 100 integers. Okay, so that's one possibility, that you are working with integers in some company or whatever, and then you say that our numbers are never going to be larger than, let's say, a few trillion. Okay, so let's try all of them. For all of them the statement is true, so we change our statement. Instead of saying that this statement is true for all integers, I'm going to say this is true for the first 10 million integers. Okay, but how about we want to prove it for all integers? In that case, how we do it? How do we divide it into cases? Again, that will not prove it. Okay, that will prove it for that sample set. Okay, that will prove it for that particular sample set जो आपने pick किया. How would I go about proving this statement for all integers?
So we know that it is true, then, but why should we prove that it is?
How do you know this might be wrong? Just because I say it doesn't mean that it's true. That would be kind of proof by authority or something, that he said it, okay, it must be true. Okay, just because someone says that this statement is true does not make it true until or unless you see the proof of it. क्या?
If we divide n on both sides,
क्या?
one is greater than
I'm hearing you. You are on the right track. But what I'm looking for is kind of cases. What kind of cases can I make that would kind of solve the problem for me?
points में number लेते हैं.
So I'm only talking about integers, right? So we don't need to worry about it.
Greater than or equal to
What?
n square minus n is greater than or equal
n square minus n is greater than, that's the same statement for it. Yes, okay. You want to say something? Bolo? Oh, again, that's not the case, right? We are only talking about integers. Someone, you want to say something?
Sir, I was at 0.5 plus gradient and
But again, we are not talking about, so we are talking n to be an integer, right? We are taking n to be an integer. Alright, so the cases, again, this was an unfair question, right? क्योंकि अभी तक मैंने जो आपको cases दिखाए हैं, they take the whole domain, उसमें से हर member के लिए. Cases you could do here is, you could take one case only for the negative integers. You can take another case only for the positive integers, and you can take another case only for 0. Okay? You prove these three cases, which are evidently easier than the proving the original statement, and then your whole statement would be proven. Okay? So you have three cases. You can have n as a positive integer, you can have n equals to 0, and you can have n less than 0. Okay? In all of these cases, the statement is true. Again, this particular thing is not a proof. Okay? It's kind of proof by intimidation or authority. The point I'm trying to make on this slide is that this is one possible thing, that you kind of partition your domain into multiple sets. They could be very big sets or infinite sets themselves, but they might be easier to handle compared to the whole set. Okay? On the same page? Okay? How about this statement? There is no solution in integers x and y for equation x squares plus 3y square is equal to 8. So, I mean, this is again a different flavor of case by case proof. Okay? Just think out of the box. How again this is an unfair question, because यहाँ पे जो case by case proof होगा, that would be completely different from the two examples we have seen so far. Okay, but again I'm just kind of nudging you towards the right proof. I'll help you. Just throw out your ideas. 3 or 5. Okay, we have time. So from the previous example and from your general knowledge, you can start by saying that I don't need to check the whole set of integers. I only need to check for non-negative integers. Okay, because x square and y square is going to be same for negative integers as is it for positive integers. Okay, so I only need to check 0 and positive integers. That at that point the equation does not have a solution. Okay, and I'm again looking for integers, right? I'm not looking for points. Yeah.
3y squared is always greater than 12 for all values.
Okay. Yeah.
So it can't be less than.
Yeah. That's perfectly exactly what I was looking for. Great. So what you do is you start with 0 for both x and y, then you try it, x equals 0, y equals 0. Okay, and this will give you something which is smaller than 8, which is great. That's what you want, right? You don't want it to be equal to 8. Then you go and check 0, 1, and then you check 1, 0, and then you check 0, 2, 2, 0, 1, 2, 2, 1. You keep doing it. At some point your left hand side would become larger than 8. Okay, at that point you can conclude that for anything larger than what I'm considering right now will always be greater than 8. Okay, and that's it. So you make a bunch of cases. You'll see how many we have. So for example, this is it. You check 0 and then you check 0, 1. That's less than 8. This is less than 8. This one is less than 8. This one is less than 8. Anywhere you consider a 2, either at this point or at this point you would exceed 8. Or at this point you claim that if I pick any numbers larger than 1 and 2 for x and y, I would always get something larger than 8. And that's it. That would be your complete proof. Okay? So you would get 1, 2, 3, 4, 5, 6. 6 cases, okay? And when you are doing the 6th case, you can say anything greater than equal to 1 and anything greater than equal to 2 for y, and conclude the same statement that this is going to exceed 8. All right? Yeah.
अगर हम x ले
Yes.
y मान लें,
Sorry, दोस्त बोलो.
x is equal to 2,
Yes.
y is equal to 1,
Okay.
a less than 8.
Oh, that's less than 8. Yeah, that case is also missed. I think you need to add that case. Yeah. You need to add the case when x is 2 and y is 1. At that point you get 7, I think, which is less than 8. Okay. Oh, x is 2 and y is 0. That's also true. Okay, good. Okay. Yeah. So any time when y is greater than 2 and any time when x is greater than 1 and y is greater than 2 is going to be the last case. Okay.